In this set of videos, we are going to take a look at how we can emulate the behavior of a larger system and what role that plays in designing large digital systems and combining them with the appropriate software that is required for that. So, some of the objectives of what we are going to be looking at is, first we want to understand the difference between simulation and emulation. I will be using a tool called Renode for most of this, for most of the demos that we have over here. And Renode is, as we will see later, a system level simulator. What we will start off is with what we call bare metal, where essentially we just have the CPU running code directly. You have a program counter that points at a certain piece of code and it starts executing. This is, as we know, the normal mode in which microcontrollers work, and it's the starting point for anything that we want to build. But Renode is not restricted to that. It also allows us to emulate full Linux systems that are booting on a virtual machine. And in order to understand that, we'll have to go through a little bit of the process of how to compile the Linux kernel. Now, this is going to be a very sort of quick demo in the sense that I'm not really going to get into any of the details of how the kernel works or even of the standard practices for developing anything new. The purpose of this course is not to sort of teach you how to become a kernel developer. It's just so that you understand enough about the Linux kernel so that it can be used in practical contexts. As we will see later, that will primarily be for building drivers for custom devices that we are trying to attach to our system. But right now in this set of videos, it's going to be very basic, right? Just an existing Linux kernel, how do we get it to compile, how do we load it into the emulator, and how do we run it? And finally, we will take the demonstration module that we had from week 3, which is basically a sort of interface to the smart timer, and walk through the process of how that can in turn be connected with Renode as a peripheral and then used for emulating a complete system along with appropriate peripherals. So, first things first, there are two terms over here that we will repeatedly be using. They are very closely related, so it's one of those things where there is potential for slightly misusing the terms in the sense that we may say one when we actually mean the other, but it's sort of worth understanding a little bit of where the primary differences lie, right? Now, so far we have already looked at this concept of simulation, and that's primarily in the context of Verilog simulation, right? So for example, we don't usually say that we are simulating a C program, we say we are executing a C program, whereas we don't say we are executing a Verilog model, we say we are simulating it. Now the reason for that is because what we are actually running in the case of the Verilog model is we have a model of the system behavior and we are trying to mimic that behavior, the what, the functionality, not necessarily the how. In other words, I don't really care whether the underlying Verilog got converted into a set of gates or function calls or it was translated into C and then run. The point is that I have a certain expected behavior which is usually defined in terms of the mathematical equations, the Boolean functions, and I want to make sure I can evaluate those and move forward. And Verilog simulators are the ones that we are familiar with so far. What do we use them for? We use them, for example, to track changes in signals, and we use some kind of a mathematical model of the gates. It could be behavioral, right, where we have an always block, or it could be gate level, where we literally instantiate AND gates, OR gates, and so on. And in general, the speed at which we simulate is unrelated to real world timing. We are interested in, we usually have some notion of a clock, but even the clock after all is just a signal within Verilog, right? We have some notion of so many nanoseconds passing. There is an internal notion of time within the Verilog simulator, but as such it need not have anything to do with how time passes in the outside world. Okay. To summarize, simulation is a slightly abstract concept. We are concerned with the model of the system behavior. Okay. So what's this other term that we come across on a regular basis? This is emulation, right? And by emulation, we usually mean something a little bit more focused than what you would have in simulation, right? And what I mean by that is, for example, we could think of recreating the exact behavior of a system. Now, of course, that term exact is problematic, right? How do I define exact? In other words, if I simulate a Verilog module right down to the gate level, I actually have a very close approximation of how the system is going to work in hardware. The only real difference is that every time that I evaluate a gate, for example, there is some function being evaluated behind the scenes, right? But it does not necessarily correspond to the transistors and other various aspects that are there inside the gate. Now, emulation also works at a certain level of abstraction. I do not plan to emulate the behavior of logic gates by going all the way down to transistor circuits. However, what I would like to do is to emulate the behavior of larger systems, right? And an example of that would be, let's say I have a CPU core that I have designed. I have some kind of peripherals, maybe it's a UART, there's a timer, there's some kind of video display unit, right? A few different peripherals that can be attached to this particular CPU. And I then want to be able to emulate the behavior of this entire system. What do I mean by emulate? I should be able to run at the instruction set level, meaning that each individual instruction that would normally be executed by the processor, I should be able to execute it on my emulated model as well and get the same behavior, right? Now, arguably, if you actually had the complete Verilog for a system, right, and you just run the Verilog simulation, in some sense that's also emulating the behavior of the system, right? However, when we talk about emulation, we usually talk at a slightly higher level of abstraction. I do not want to spend that much time doing a fully gate level accurate simulation of a CPU. Instead, I can abstract it out. Rather than going and considering all the individual flip-flops, AND gates, full adders and so on involved in incrementing the program counter, I can just write PC equal to PC plus 4 and go to the next address, right? So, emulation, once again, the goal is that it should be an accurate model of the system behavior, but once again accurate at what level, right? Primarily what we want is instruction set, the instructions that are executed by the CPU should be accurately modeled within the system. We sometimes call for something called cycle accurate emulation, and this usually comes in when we are talking about co-simulating. We have some hardware, we have some software, and we want to sort of combine the two into one single simulation. So, the end goal of emulation is to verify functional equivalence with the system, right? We want to know that whatever we are emulating behaves the same way as what the system would be like when it is finally actually implemented in hardware. As I said, both of these terms are very closely related. You could think of a very detailed simulator as effectively emulating the behavior of the system, but usually emulation abstracts away a lot of that and tries to do things a little faster so that we can actually do things like emulating a complete system without having like the ultimate levels of slowdown where you are executing maybe only a few hundreds of clock cycles per second, whereas the actual system should be running in like millions of clock cycles per second. Okay. So, now having said all of this, let's think back and take stock of what we already know. As far as simulation is concerned, we know that we can use tools like either iVerilog or Verilator, or there are a number of other commercial simulators, right? And they can all be used in order to run Verilog code. Now, as I also just pointed out, that would be probably very slow when we are trying to, let's say, boot Linux on an actual model of a CPU. So instead, what I would like is to abstract away that model of the CPU to a much higher level where I can actually execute hundreds or thousands or possibly even millions of the instructions that are given to the CPU per second, right? And therefore get close to real-time execution, or maybe not close to real-time, but at least like fast enough that we can actually make meaningful observations about the behavior of the entire system, right? So, the best way to understand exactly what emulation means is to actually go through and work with a concrete emulator, and that's what we are going to be doing in the remaining videos.